Hello, everyone. Greetings of the day. The authors and invited guests, welcome to Technical Session 12E. Myself, Prashi, and this session will be moderated by me. On behalf of Global Knowledge Research Foundation and GIA Scholastics, it is my great pleasure to welcome you to the 11th International Conference on Information and Communication Technology for Intelligent Systems, ICTIS 2026, Bangkok, Thailand. The 11th edition of this conference is being organized in a hybrid mode. The physical event will be held tomorrow in Bangkok, Thailand, and the virtual event is being held through Zoom from 9th to 11th of April 2026. I hope you will enjoy the knowledgeable and interactive session through the day. In this session, we have 10 presentations. Each presenter will be given 10 minutes for the presentations and 2 minutes for question and answers. On 9 minutes, I will be raising a gentle reminder. There will be another request to all our participants. Please stay connected with us till the closing remarks. If you have any queries or any updates, you can write it to me in the chat box given down below. Just before we start our session, I would like to introduce you all to our session chairs for this session. Our first session chair is Professor Sylvia Micheni. Welcome to the session, ma'am. Dr. Sylvia is an associate professor in the Department of Computer Science in the University of Turin, Italy, with approximately 9 years of experience across academia and industry. She focuses on sustainable and data-driven technologies. Her research interests include digital twin, green public procurement, circular economy and waste management, and smart infrastructure supporting environmentally responsible innovation. We welcome you to the session. Would you like to say anything before we start our session today?
Just good morning, everyone. I'm really glad to co-chair this session, and you said everything, so that's all.
Thank you so much, ma'am. Thank you. I would like to introduce you all to our second session chair as well. Our second chair is Dr. Sunil Sangwe. Dr. Sangwe is a professor of Department of Artificial Intelligence and Data Science, Vishwakarma Institute of Technology, Pune, India. He has more than 22 years of experience in teaching of academics. His area of specialization is in network security, data mining, software engineering, data science, and analytics. Sir, we welcome you to the session. Before we start, would you like to say anything as an opening remark to our participants?
I guess you are muted, Prachi.
Oh, I'm really sorry. I would like to call upon our first presenter, Sir Vedant Vipin Joshi, presenting a paper on the title, A Multimodal Framework for Integrated Software and Hardware Project Orchestration. I request you to kindly take over. Sir Joshi. All right. Anybody who is on behalf of Sir Joshi presenting over here? If anybody is there, you can take over with the presentation. All right. So as we don't have him right over here right now with us, we'll just take we'll call out our next presenter. Our next presenter is Samiksha Ganesh Izgade, presenting a paper on the title AI-powered wearable devices enhancing human communication and interaction using intelligent systems. I request you to kindly take over with your presentation, please.
Hello, good afternoon. Hello.
Hello. Yes, ma'am, you're
Yeah,
audible.
good afternoon. Yeah.
Good afternoon.
I'll share my screen.
Yes.
Are you able to see my screen?
Yes, ma'am, we can see your screen.
Yeah, should I start?
Yes, please.
Yeah. Good morning, respected panel members and everyone present. My name is Samiksha Zagre, and today I will be presenting our research paper on AI-powered wearable devices enhancing human communication and interaction using intelligent systems. This work has been carried out under the guidance of Dr. Suman Madan at Atlas Skilltech University. Our research focuses on how intelligent wearable systems can move beyond passive data collection and actively support real-time human communication. I'll briefly walk you through the structure of the presentation. We will begin with the evolution of wearable technology, followed by key communication challenges. Then, I will discuss the uh, foundational technologies, multimodal sensing, and system architecture. After that, I will explain the AI ML techniques applications through tables. Finally, I will cover the future scope and conclusion. The evolution of wearable devices. Wearable technology has evolved from a simple fitness tracking device to intelligent systems. Earlier, devices focused only on collecting data such as steps and heart rates. With the integration of artificial intelligence, machine learning, and Internet of Technology, modern wearables now interpret and respond to human behavior in real time. This marks a shift from passive data collection to active communication system support. This diagram represents the overall architecture of the intelligent wearable system. At first, wearable devices act as IoT edge nodes where data is collected through various sensors. This data is then pre-processed and transmitted for further analysis. Edge computing also allows real-time responses with low latency, while cloud platform handle shortage and advanced processing. This hybrid architecture ensures both stability, scalability, and responsiveness. Nowadays, humans face a lot of communication challenges. So here I am addressing a few of them. Despite advancements, several communication challenges still exist as we know. Language barrier and difficulty understanding emotions or social cues is the major issue. Individuals with hearing or speech impairments face accessibility limitations as well. Additionally, many systems collect data but fail to provide meaningful real time assistance. These challenges motivated our research. Foundations of intelligent wearables. Artificial intelligence enables interpretation of complex multimodal systems. Machine learning also allows systems to learn patterns and adapt over time. The Internet of Technology (IoT) ensures connectivity and real-time communication for edge nodes, exchanging data. These are the three core technologies that build a system. Together, they form the foundation of intelligent wearable systems. Now, I will proceed with the multimodal sensing. Multimodal is essential for accurate understanding. Accelerometers and gyroscopes are used for activity and gesture recognition and study. PPG and ECG sensors for cardiovascular, stress, and emotion related parameters mostly used in medical fields. Microphones and contextual sensors capture environmental and interaction data. Combining multimodal sensors inputs improves accuracy as well as robustness of the system. This diagram illustrates the workflow of the system. First, as you can see, the data is collected through variable sensors such as motion, audio, and physiological sensors, and also smart sensors like IMU, ECG, and accelerometer. First, data is collected and then it is processed further. AI processing is applied, including signal processing and feature extraction. Machine learning models like CNN and LSTM analyze patterns such as activity, speech recognition, and emotion recognition. Finally, the system generates output for intelligent applications like communication assistance and context awareness, which improves user interaction. This enables real-time decision making and interaction support among people. Now we're going to talk about system architecture of intelligent wearables. The system flows are distributed. The system flows distributed architecture combining edge and cloud computing. At the level edge, wearable devices perform local processing for low latency and immediate feedback. Data is then transmitted to the cloud for storage, deeper analysis, and model updates. The hybrid approach ensures both responsiveness and scalability of edge cloud computing. It supports applications such as health monitoring, accessibility, and intelligent interactions. Key AI techniques. Let's go through the AI techniques. Now, uh, sorry. Yeah. Now I will explain the diagram which shows the workflow of AI-powered wearable systems. The system consists of three main stages. First is, okay, just a second. Yeah. Uh, First is wearable data acquisition, where data is collected using different sensors such as motions for movement, smart sensors like IMU or ECG for physiological signals, and microphones or cameras for environmental input. Next is AI processing and analysis, where the collected data is processed using techniques like noise filtering, and feature extraction. Machine learning models are then applied to identify patterns related to activities, behavior, and speech. And then finally, the processed data is used in intelligent applications such as communication assistance, um, emotion, emotion detection, health monitoring, and improved user interaction. Overall, this system enables real-time analysis and helps wearable device provide meaningful and intelligent support to users. Yeah. AI ML techniques. Uh, Different AI and machine learning techniques are used. Supervised learning methods such as SVM, KNN, and random forest are used for classifications like gesture classification and activity classifications. Deep learning models like CNN, RNN, and LSMT for high accuracy and in emotion detection and physiological signal analysis. Pattern recognition techniques combine multiple sensors input to improve robustness. Predictive analysis enables early detection of stress and anomalies, which is a good sign for early warnings.
I'm sorry to
Now I
interrupt
will,
you. However, we have crossed our 9-minute mark. I request you to
oh,
kindly conclude as soon as possible, please. Thank you.
yeah, sure. Now I will go further to applications and challenges. Okay. AI-powered wearable systems offer significant benefits. They enhance communication, provide accessibility support, enables activity recognition, and improves healthcare monitoring. However, challenges such as energy consumption, privacy concerns, and system reliability still exist. Overcoming these challenges is critical for real-world adoption real-world adoption. So this table represents key application areas of AI-powered wearable systems. Future of human-centric wearables. Looking ahead, wearable systems are evolving into intelligent assistants capable of understanding speech, gestures, emotions, and context in real time. By improving energy efficiency, scalability, and privacy, these systems can unlock their full potential. High-centric design will play a key role in enhancing user experience and trust. The research paper presented is supported by multiple references studied and existing literature in AI wearable systems and human-computer interactions. In conclusion, AI-powered wearable systems can significantly enhance human communication and interaction through intelligent and real-time assistance. While challenges like energy efficiency, privacy, and scalability remain, they also open opportunities for further research. As a first year student, this is our initial work and we aim to continue exploring and improving this area in future. Thank you.
Thank you so much for your presentation. I'll ask our session chairs, do we have any questions? Yes, ma'am.
Yes, can I?
Yeah, yeah.
Good presentation, and I'd like to know how do you balance intelligent personalization with the privacy and real-time usability in the wearable system?
I'm so sorry. Can you please repeat the question?
Sorry,
I didn't hear you. Can you please repeat the question?
I didn't get it. I'd like to know how you can balance the personalization with the privacy and real-time usability of the wearable system, your system.
Stabilization, privacy, and user interaction, right?
Yeah.
So stabilization is okay. Balancing intelligence, stability, and privacy and user interaction is this was our basic research. So we got to know what we studied from the research paper. So the devices are already intelligent. So we will use AI models which recommend and predict to do these analysis. So uh, systems as they should not crash or behave unpredictably. So the stability for like error handling or testing can be improved by complex AI system and that can reduce stability if possible. And about user interaction,
Mhm.
um, data encryptions and user consent, more personalization or more detailed encryption can be done by collecting only what I need. So that is how you can preserve the privacy for user interaction. And for small scenes or voice comments like small interfaces, personalized responses using AI avoid like overwhelming users with too many alerts. So these are the things I can improve in my research or the model which I make further.
Okay, good to know. Nice.
Yeah. Thank you so much, ma'am.
Ms. Samiksha, we have one more question from Sir. I guess there's some problem with Dr. Sangwe's mic. So he's asked your question in the chat, asking, can you focus on your contribution in this work?
Um, my contribution in this work was, I'm sorry, I couldn't understand the question.
He has written it in the chat as well. Uh, you may see it. He's asking
Yeah, yeah, yeah.
how you were contributing to this particular work. That is what he's asking.
Yeah. So I basically went through a lot of research papers, um, as I have shown in the PPT, and through those I made a new, uh, I mean, the sentences, I reframed them and I researched more about a few of the topics such as applications and uh, like multimodal sessions. So I went through all these very fluently. So my role was to, are you talking about the research paper, right? Or the model?
So make sure that was what Sir was asking. However,
Okay.
because he has some glitch with the mic, I hope,
Yeah, yeah,
Sir, you are happy with the answer. All right.
yeah.
Thank you so much, Samiksha. Thank you for answering the
Thank you
questions.
so much.
Now, let us invite our next presenter for this session. Our next presenter is Adnan Hassan, presenting a paper on the title Comparative Study of Emerging DL Models in BTD. I request you to kindly please take over with your presentation.
Good afternoon. I hope I'm audible.
Yes, you're audible.
Okay, I'll quickly share my screen. Okay, I hope my uh, presentation is visible.
Yes, sir, your presentation is.
Okay. Okay, so good evening again. My name is Adnan Azam and I'm from Kalinga Institute of Industrial Technology. And I'll be presenting my paper on comparative study of emerging DL models in brain tumor detection. Our paper ID is 1339 and my co-authors are Ishan Mishra, Jyotiska Bose, Jay Kumar, Jada Vishwa Chaitanya Sai, Kaf Akhtar and Dr. Ranjita Kumari Das. So uh, let's start with the problem statement. So, brain tumor detection is, as we know, very critical. So, the MRI scans are very critical for early diagnosis and treatment planning. However, the manual interpretation is very time consuming and also prone to human error, and also is very highly dependent on the expert radiologists because they can introduce variabilities. The existing CNN models struggle with generalization. There is no standardized comparison that is available. So there is a limited research. There is a research gap in that sense that the traditional models, there is no standardized comparison between the traditional and modern CNN architectures, and many of the studies rely on small and heterogeneous MRI data sets, which leads to inconsistent pre-processing and yeah, so which leads to limited proper evaluation and model generalization. Now our research objective is to compare five deep learning architectures, that is VGG19, ResNet 50, DenseNet 121, Convex Tiny and EfficientNet. And we are to identify the most effective model using multiple evaluation metrics. Now, if we talk about the dataset composition, we have actually curated a dataset of 13,692 MRI images, and we have curated it by ourselves from public sources. And then we have done balanced classification between tumor and non tumor. And then we have done pre-processing, which includes resizing and normalization and data augmentation. This is so that there is less biasness amongst any of the images. For example, like less biasness amongst for high resolution images. Another methodology, we have applied pre-processing and stratified sampling. Transfer learning was used with pre-trained CNN models, and we have fine-tuned it on our dataset. Our training used Adam optimizer and cross entropy loss with consistent pipeline. The model architectures that we have used are VGG19, ResNet 50. Now, these are the baseline models. These are the traditional architectures. And the modern architectures are DenseNet 1-to-1, ComNext Tiny, and EfficientNet. Now, our experimental setup is that our models were trained under a uniform setup using transfer learning. Evaluation were done at 5 and 15 epochs using accuracy, precision, recall, F1 score, and confusion matrix. Now, here are the results of our setup. On the right hand side, as you can see, is the confusion matrix, and on the left hand side is kind of the summary. And some of the key pointers are such that VGG19 is one of the traditional models, and it did not perform that well after 5 epochs, but it did pick up at the 15 epoch. And amongst all the models, EfficientNet has done the best with 92.19% accuracy, F1 score. Now, with our results, we can note that EfficientNet has demonstrated superior feature extraction and generalization, and Connex and DenseNet 1-to-1 has also shown consistent performance. As you can see, they have given 91% accuracy each with 5 epochs, and ResNet has done better with 15 epochs. Now, coming to the conclusion, I would like to conclude with saying that the modern deep learning architectures have actually done well as compared to the traditional architectures, and also that EfficientNet is the best performing model. And this study provides us a benchmark for automated diagnosis. Future work can include explainable AI techniques, multi-class classification, and validation on real-world dataset. So that was it from our side.
Thank you so much, sir. Now I request our session chairs. We have any questions? Do I request you to kindly?
Yes, I have one question. I'm audible?
Yeah, you're audible, sir.
Yeah, thank you. So I have one question. So what are the features you have used for the classification to identify either the sample is having a tumor or non-tumor? So what features you have used for the classification purpose? Okay, over to you. Thank you.
We have used texture, intensity features, shape features, edge features, like the usual CNN models uses.
Okay. Because whatever the architecture you have used,
Yes,
and
sir.
from that architecture you have identified that one of the architecture is going to generate the good result as compared to the
Okay.
other four one. So
Yes,
in
sir.
each and every architecture, they are following the same type of data set, same number of samples, as well as the same process you are
Yes.
following.
Yeah, we are using the same
Okay.
process for each of them.
And with the same number of features.
Yes, sir.
Okay. Thank you.
Okay.
Good
Ma'am, do we
afternoon,
have
madam.
any questions from your end?
No question from my side. Good presentation.
Thank you.
Thank you so much, ma'am.
Good
Thank you so
afternoon,
much for your
madam.
presentation, sir. Yes, sir.
Good afternoon, madam. This is Sheikh Janbasha, paper ID 1087. Due to urgent meeting, I could not present my paper on previous session, madam. Can I present now?
Sir, as I told you, because it was their previous session, sir. So now we have to
Yes.
accommodate you in the last, or if somebody is absent in the last, I'll be able to take you, sir. I request you to
Okay,
kindly be
madam.
informed about the same. Thank you.
Okay, madam. Thank you so much. I will wait.
Thank you so much. Now moving on to our next presenter for the session. Our next presenter is Jyoti Chandel, presenting a paper on the title DODS Attacks Detection Using Hybrid Feature Selection Methods and Federated Learning. I request you to kindly take over with your presentation, please.
Good afternoon, ma'am.
Good afternoon.
Is my screen is visible?
Yes, ma'am, it is visible.
Good afternoon, everyone. I'm going to present my paper on DDoS attack detection using hybrid feature selection methods and federated learning. And my paper ID is 1306, and my co-author name is Meenakshi Mittal. And the content I'm going to cover in my slides are introduction, literature survey, proposed methodology, experimental setup, and result discussion, conclusion, and future scope, and the references. So firstly, I'm going to share what is DDoS attack actually. It's happened when an attacker send a large number of requests to a server website from multiple systems and overload the server and making the resources unavailable for the legitimate users. So in my paper, I use federated learning for DDoS attack detection because various traditional methods have been proposed for DDoS attack detection. But the thing is, the method has primarily rely on deep learning approaches, and they require data to be collected at a centralized location. And deep learning models are further demand large volume of network traffic data for effective training. And the organization are usually unwilling to share their network data because of the privacy and the security concern. So to overcome this challenge, this research work employed with federated learning, and the federated learning is enable the model to train on local devices and share their parameter instead of the raw data to a centralized location. And in this approach, collectively train a shared model without exchanging their original data, thereby the maintaining the data confidentiality while strengthening the overall attack detection capability. So the contribution of my paper is firstly, I do the hybrid feature selection approach for DDoS attack detection, and later I divided the dataset in two scenarios. First one is mildly non-ID dataset, and the second one is strongly non-ID data. To analyze the robustness and performance of the proposed federated learning approach under varying level of data heterogeneity. And then I used a random forest model to train using federated learning over the multiple participating client. And then I evaluate the performance under both the scenario. So here's the relative work, and in reference 5, the author also used federated learning for intrusion detection, and they got accuracy around 98%. And in the second paper with reference 6, they also used federated learning for intrusion detection, and they got the accuracy nearest 99.89. And I sum up the literature review in this research gap, which I find out that federated learning has been widely used for DDoS attack detection. However, many existing studies do not clearly explain how data are distributed across clients and analyze the presence and the effect of non-ID data, as a non-ID data distribution is strongly influence the federated learning performance. So this is the methodology diagram which I used in my paper. Here in phase 1, I used hybrid feature selection method where I used mutual information, permutation importance, and then greedy cross-validation method for feature selection over here. And in phase 1, when I got my features, later I used a federated setup. And in federated setup, I have taken 15 clients and one server, and I use fed average here for aggregation. And in this scenario, I performed two experiments over here. One is with where I partitioning data in strongly non-IID data, and second one where it's a mildly non-IID data distribution. So in my paper, I used CIC IoT 2023 dataset. I work with it, and I used multi-class classification over here where I took 6 classes. And in phase 1, I use hybrid feature selection over here. And initially, I use a filter-based method, which is mutual information. And I employed it to compute the relevance score for each feature. And later, I use permutation feature importance, which is also used to quantify the contribution of each feature with respect to the target class based on the performance degradation. And later, the score obtained from the both methods are normalized and combined using a weighting score mechanism. And after that, I use a greedy wrapper-based selection method where the feature are iteratively added from a ranked list obtained by the weighted scoring strategy of a hybrid MI and PFI score and evaluated using a stratified cross-validation with a random forest classifier. And in phase 1, when I use hybrid feature selection method, later I have 39 features in my dataset, but after hybrid feature selection, I got 15 features. And in phase 2, I used federated learning setup over here, and where for the distribution of data I used Dirichlet distribution over here. And this is the in context of federated learning, it's primarily employed to generate non-IID data partitioning in order to simulate heterogeneous data distribution across multiple clients. So the concentration parameters plays a crucial role over here because it control the level of heterogeneity across the client. So if the alpha value is less than 1, then the Dirichlet distribution assign highly skewed class distribution to each client. As a result, most data records stored on the client are drawn from only one or a few classes, which lead to a strong class imbalance. And if alpha value is 1, the client distribution are relatively balanced and or average. And if alpha is greater than 1, it increases more balanced class distribution across clients, leading to milder non-IID behavior. So in my methodology, I performed the experiment in 2 scenarios where I use the alpha value is as 0.5, which is used at mildly non-IID data distribution. And in second scenario, I used the smaller value, which is alpha is equal to 0.1, which used to simulate extreme non-IID distribution. So this is the table where which present that how heterogeneous data it produced. Like you can see that if alpha value is 0.5 and each client have each class over there. And in second table 4, when the alpha value is 0.1, it create a heterogeneous data where some classes are absent on some clients. So the results of my experiment I got here that the proposed approach used random forest. So in multi-class classification, when the data is mildly non-IID, I got the accuracy of 99.69%. And later when I goes with the strongly non-IID data distribution, where the value of alpha is 0.1, the accuracy is drop little bit, which is 0.9836. And here I show it the difference between both of them in a graph over here. And later I also compare the convergence of both the experiments. And in next slide in figure 4, I also compare the federated learning with the centralized approach, where I find out that there is a lot of difference in the performance of centralized and federated learning. Like you can see that centralized SVM model achieved the accuracy of 0.9970. And if I not go with the high heterogeneity, I can get 0.9969 with the alpha value of 0.5. But later on, when I go with the high strongly heterogeneity, the result is drop a little bit, which is 0.9836. And the conclusion and future work, the experiment in strongly non-IID setting, I achieved the accuracy of 98.36, which represent a slightly reduction as compared to the mildly non-IID setting. This is because the most classes are still observed by multiple clients in the federated learning setup, which are prevent completely class absence and mitigate the negative effect of extreme non-ID data. And overall, the proposed approach maintain high accuracy and making it suitable for secure and distributed intrusion detection. And in future work, the impact of non-IID data distribution will be further analyzed by reducing the number of participated clients and studying how this affect the model ability to handle the data heterogeneity. And these are the references. Thank you.
Thank
So
you
you
so
have
much.
done a good job, I think, Jyoti Chandil. Your work is very nice. I
Thank
have was a simple question related with the value of alpha, which you are going to set for the zero point 0.1 and zero point 0.5. So
you.
what is your result for the other values of alpha? Either it is going to give the more accuracy, or your accuracy is going to be deteriorated.
Sir, actually, if the data is 0.1, means the data is
Mhm.
really heterogeneous among the client. So the accuracy is
Okay.
dropped because every client is not able to see in every class.
Okay.
So the accuracy is dropped. But if every client have every class in IID data, that is less
Mhm.
heterogeneous. So the result is automatically, sir, comparatively non-IID can be good.
Is there any effect of the hardware parameters which you are going to suppose to choose for your local
Yes, sir. Yes, sir.
workstations? Yeah.
Yes, sir, absolutely. The if I sir, this work is done in a simulated manner, but if I go within
Okay.
a real world setup, a real world test bed, that then the hardware of every client influence the accuracy over here.
Okay. Thank you. Nice.
Ma'am Mishini, do we have any questions from your end?
No, thanks. Good presentation and good work.
Thank you so much, ma'am. Thank you so much for your presentation, Shindel. Now we'll call upon our next presenter. Our next presenter is P.N. Diorukar, presenting a paper on the title Design and Development of Artificial Stuttered Speech Corpora. I request you to kindly take over with your presentation, please. So, Diorukar or anybody from the authors, if you are available with us, I request you to kindly take over with the presentation, please. All right. So I think that nobody has joined yet for this particular paper. I'll call upon our next presenter, Sir Domenico Diola, presenting a paper on the title Frugal Digital Twins, a Holistic Framework for Rural IAQ Management through IoT and BBFILI integration. I request you to kindly take over with your presentation, sir.
Hi, everybody. I hope you can see me and hear me properly. I'm
Yes, sir.
going to share my screen at the moment. Just a second. Okay.
Yes, sir.
Okay. Can you see my screen now?
Yes, sir. We can see the screens.
Okay, great. So, I'm cleaning my screen. Okay, great. So, welcome everybody. Thanks for inviting me for this presentation. I am presenting a framework for frugal digital twins. What is it about? We are looking at a method to manage indoor air quality in rural villages by combining low-cost IoT sensor with biophilic design. The research addresses a significant gap in public health intervention, focuses on resource-limited settings where traditional high-cost building management systems are not feasible. Okay. Indoor air quality is a critical determinant of the health in rural areas. It is calculated by the World Health Organization a cause of 3.2 million deaths every year for low quality of air because of low income community has a high use of wood, crop residue and coal for cooking and heating, which leads to extreme levels of fine particulate matter. So our goal is to create sustainable and low-cost solutions that do not depend on expensive HVAC infrastructure, which is often unaffordable or practical in these regions. Our case study is an hamlet of Arischia in Italy. Because this very specific area has difficult for survey of different building, and because of the complexity of working this area due to an earthquake which struck the area in 2009, it has been made up a system to actuate survey through an indirect method. It is a method which works on digital data that build polygons from the public dataset, interpolate them and project them onto the 3D terrain so that it is possible to rapidly survey remote areas at almost no cost. The first step is to create an accurate 3D model of the rural village without costly on-site survey, as we were saying. The first step is to create a GIS to NURBS parametric workflow. We are taking open source regional DTM data, building footprints, and algorithmically generate a continuous NURBS surface in rhinoceros and grasshopper. Unlike traditional faceted meshes, NURBS offer the geometric continuity needed for reliable airflow and solar exposure analysis. To make this model accurately, we convert the NURBS geometry into BIM entities with specific tools like Rhino inside Revit, and we give them property with a specific application, which is MKS DTech build, so that at the end we are able to assign a real-world material characteristic to digital masses, transforming a simple geometric model into a functional data environment. Our hardware is an open source hardware which is made on Arduino ecosystem. We are using the MKR Wi-Fi board for transferring data to the Wi-Fi network, and an ENV shield, which is this board, which monitor temperature, humidity, pressure, and a specialized SA sensor for the CO2. Data is sampled every 10 minutes so that we can have an accurate measure of the area. It is vital to distinguish between digital shadow and digital twin. A shadow is a passive mirror where data flows only from the physical sensor to the digital model. A true digital twin is active when the model sends command back to the building. In rural homes, automated actuators like motorized windows are too expensive, so we use a human-in-the-loop strategy. Here, the digital system provides feedback to the resident, who act then as actuator by manually open the window. Residents interact with a simple visual interface, an LED on the Arduino, which is just a light that changes color based on CO2 level. It turns red when indicates that the area quality exceed 1,000 parts per million of CO2. And this is a shoulder with the prompt to open the window with lower indicator for CO2 in yellow and green shows the quality of the the area. Residents of the hamlet act in this way as a human in the loop, which means that when they see the red light, they open the window. When there is the light green, they can stay with the windows closed because the area can be in some way good. So the threshold where this thing is located is in terms of 700 part per million of CO2 and 50 micrograms for cubic meter for PM 2.5 for fine particulate. This is a threshold defined by the World Health Organization, which is safety for human being. To achieve the result, an incredible series of tools, of digital tools has been activated, but the most important tool is the phytoremediation. This system introduces a vegetal essence into the environment, which acts both as a mediator for CO2 and humidity, and it creates a system that acts as a lung for the building. So this is a system that tries to breathe and try to mitigate the air for the whole system. Actually, we are currently testing the actual effectiveness of this plant by using controlled plexiglass boxes where the upper prism contained the plant and CO2 sensor, while the empty one on the bottom has as a control. This helps quantify exactly how much phytoremediation contributes to overall in air quality sensor. The results are really good in terms of sustainability because all the Arduino monitoring and biophilic integration consumes an amount of 20 watt per application in comparison with a conventional average condition unit HVAC unit, sorry, which account for 2,000 euros watt. So it is very important because we are not getting worse urban area, but we are trying to work with very low cost element, very low energy consumption. Of course, it is important to understand that the contribution is very low for a single plant which has this single disciple activity, but in thinking it on upscale, it can have a really good impact on the environment. What it is the plant that we choose to use in the aid of biological researcher. We choose the Epiphrenium aureum, which most common name is golden pothos. It is a plant that has a very high resistant, and it is very easy to maintain, and it can have a great passive action on the house. It is important that this action of digital twin is activated by the people that open the window in change of a system that open it automatically in the system of looking at the sign that says when it is important to open or close the window. And
I'm
it
really
is a
sorry to
main.
interrupt you, sir. However,
Yeah.
we have crossed our 9-minute mark. I just request you to kindly wind up the presentation as soon as possible, please.
Yes, I've got the last slide.
Okay,
This is the
sir.
conclusion. In conclusion, the holistic framework provides that we can significantly reduce pollutant exposure in rural settings without energy-intensive appliances. Our next step involves a year-long data collection phase and expanding the pilot to more homes. We believe this frugal approach can empower rural communities to achieve a healthy balance between modern comfort and resource conservation. Thank you.
So nice presentation, sir. Thank you for the presenting your work. Thank you.
Okay.
I have a question.
Okay.
Nice work, and And your framework is quite interesting as it replaces expensive automated actuation with the human in the loop strategy and also combines this with passive feature remediation. So, from a scientific point of view, how did you distinguish the contribution of occupant driven ventilation from the contribution of the plants in improving AIQ?
Yes, it is one thing which if I can share the screen again, there is something which has been stated. Okay, I hope. Okay, can you see my screen?
Not yet.
Not yet?
Now, yes.
Okay.
Yes, so the validation.
Okay. Yeah, the validation is just made up, and the boxes that I've shown, just to show the boxes, just a second. Okay. Just a second. I don't know why it is not working. Okay, great. Okay, I hope you can see my screen now. Can you see it?
Just a second, sir. It is loading, I suppose. Just a second.
Okay, great. Okay.
Yes, now we can see, sir.
Okay, great. This is one of the things that was at the beginning of the research because it was very difficult to calculate how much the plant impact on the air, so that this system is specifically used to isolate the influence of air current, because the box in the lower part is completely without current. The only air is pushed through this vent, and there is a vent which gets the air in, and there is a vent which gets the air out. The upper is maybe more clear. And we measure the impact of the absorption of air with or without the plant in a controlled environment. These are boxes which represent 1/10 of a real room. The measure are in inches, but it is just a box which is equivalent to a room. And this room has a complete control on the air ventilation because we use exactly the same vent with exactly the same area that flows in and flows out, so that we can measure with the sensor difference when there is the plant and when there is no plant, so that we can have a precise measure. We can say that for each plant, of each environment, we have an absorption of currently around 200 point of part per million in an environment without the plant. This is the differences, which is not that much, but it is very measurable. It's not something which is so small to be not measured. That's how it works. Does it make sense?
Yes, it makes sense. Quite a lot, so good work. Thank you.
Okay, thanks a lot.
Thank you so much for your presentation, sir, and thank you so much for your explanation. Now, I would like to call upon our next presenter for the session. Our next presenter for the session is Kritika Singhal, presenting a paper on the title IntelliTask, an AI-driven enterprise task management system. I request you to kindly take over with your presentation, please.
Hi, I hope I'm audible.
Yes, you're audible.
So I'll just share my screen real quick.
Okay.
I hope everybody is able to see my screen.
Yes, now it is visible. Yes.
So, good afternoon, everyone. My name is Kritika Singhal. I am from KIET Group of Institution, Ghaziabad, India. And first of all, thank you so much for considering our work. Today, I'll be presenting a work titled IntelliTask, an AI-driven enterprises task management system. So, in today's fast-paced world, the biggest challenge is not managing tasks. It's deciding what to do first, when to do it, and how to do it efficiently. So our work focuses on transforming task management system from a static process into an intelligent adaptive system. To understand this, let's first look at the problems. The current system manages tasks but don't optimize them. So currently management systems mainly focus on organizing tasks and they do not optimize how work is actually executed. One major issue is manual optimization. Teams spend significant time deciding what to do instead of actually doing the work. This leads to missed deadlines because there is no intelligent scheduling mechanism. Workload distribution is also uneven, creating bottleneck for some team members while others remain unutilized. Most importantly, these systems lack adaptability and cannot respond to dynamic change in workflow. So overall, current system manage tasks, but they do not optimize them. So now let's look at what make it more critical in today's environment. With modern enterprises, workflow have become increasingly complex. Tasks now span multiple teams, tools, and dependencies, making manual coordination very difficult. Additionally, there is a culture of remote and hybrid work environment also, which require that we can maintain alignment in real time. Manual planning is time consuming and error prone, which reduce efficiency. Therefore, organizations need intelligent data driven system, not just a tracking tool. So, based on the problems and the situation we had in hand, we are proposing a solution which is IntelliTask, which transforms the task management system from static to intelligent. IntelliTask is an AI-driven task management system designed to understand task attributes, team capacity, and changing priorities. It dynamically prioritizes tasks based on urgency, dependencies, and workload signals. It also uses predictive scheduling to estimate timelines and allocate resources efficiently. Overall, IntelliTask transforms task management from static to intelligent. So now let's look at how this system is structured internally. The system follows a layered architecture as shown here. The API gateway manages secure communication and request routing. Backend services handle machine learning processes and task execution logic. The core database store task data, user information, and system logs. This modular structure ensures scalability, flexibility, and efficient system performance. Building on this architecture, let's look at the key feature of the system provided. IntelliTask provides several key features. It performs intelligent prioritization, ensuring how impact tasks are surfaced at the right time. Predictive scheduling uses historical pattern to estimate timeline. Real-time collaboration keep distributed team aligned. Role-based access control ensures security. And continuous learning allow the system to improve over time. Now let's understand how the system actually make its decisions. The system follows a data-driven pipeline. It began with collecting task attribute like urgency, deadline, and dependency along with user behavior. These inputs are processed through feature engineering to generate metrics such as urgency score and workload index. The data is then processed and normalized for consistency. Finally, it is fed into machine learning model for prioritization and scheduling. This ensures real-time intelligent decision making. Now look at the model. So the IntelliTask uses a hybrid machine learning approach where it utilizes three algorithms. The first one is random forest, which is used for priority classification. The other one is K nearest neighbor, popularly known as KNN, which refine prioritization using similarity with past tasks. The other one is linear regression, which predict task completion time. Each model handles a different aspect, and together they improve both accuracy and adaptability of the system. With this approach, we can look at how the system performed when we evaluated the system on a data set of 500 simulated tasks. The model achieved an accuracy of 86% with balanced precision and recall. It also maintained low latency with response time under 200 milliseconds. These results demonstrated strong performance and real-time efficiency. With these results validate the model, we have also implemented this system in real life. So this is our main dashboard of the system. This slide shows the practical dashboard. The dashboard provides a centralized workspace for managing tasks. User can monitor activity, track the team presence, and receive updates instantly. Most importantly, it displays AI prioritization tasks, helping user focus on what matters most. This demonstrates how a system works in a real-world setting. So now let's look at the comparison of our system to the traditional systems. IntelliTask represent a shift from traditional to intelligent system. Traditional tools rely on manual prioritization and static workflow. In contrast, IntelliTask offer AI-based prioritization, dynamic scheduling, and high adaptability. This makes it more suitable for modern enterprises environment. So if we sums up our work, in conclusion, IntelliTask improves productivity and efficiency by automating task prioritization and scheduling. It enables data-driven decision-making and reduce cognitive load. Overall, it represents a shift from managing tasks to intelligently optimizing work. Lastly, IntelliTask is not just a task management tool. It is a step toward intelligent work environment where systems don't just track work, they actively help us work smarter. Thank you for your time and attention. I would be happy to take any question.
Thank you so much, ma'am. I'll ask our session chairs. Do we have any questions?
No, ma'am. Good work. Thank you.
Thank you so much,
Thank
sir.
you so much.
Ma'am Sylvia?
Me neither. Good work.
Thank you so much.
Thank you so much for your presentation. Now, on that note, I would like to call upon our next presenter. Our next presenter is K. Tarun Kumar, presenting a paper on the title Ransomware Detection Using Hardware, Performance Counter, and Machine Learning. I request you to kindly take over with your presentation, please.
Yes, ma'am. Am I audible, ma'am?
Yes, sir.
Wait a minute. I will share my screen. Is my screen visible, ma'am?
Just give me 1 second, sir. It is loading, I suppose. Now, yes, sir. Now it's visible.
Okay. Good afternoon, everyone. Today I am going to present our project title Ransomware Detection Using Hardware Performance Counters on Machine Learning. This project is done by our team and the guidance of a faculty of M. Nirpama Bhatt. So let's start explaining what is this project about. First, I will give a brief introduction and then discuss existing work and the problem statement, motivation, and the methodology, results, and finally the conclusion. So first, what is ransomware? Ransomware is a type of malware that encrypts user data and demands money to unlock it. Now, the main issue is that modern ransomware is very advanced. It uses techniques like zero-day attacks and polymorphism, which means it keeps changing like its pattern. So because of this, traditional antivirus systems fail to detect it. So what in our project is, instead of using signatures, we use CPU level behavior, specifically hardware performance counters, along with the machine learning to detect ransomware in real time. So now coming to the existing work, many researchers have used many machine learning models like random forest, SVM, and XGBoost. So they achieved very high accuracy, sometimes even up to 99%. But there are some limitations. Most systems are not real time. So some depend on static analysis and many ignore CPU level behavior. So our approach improves this by using real-time behavior detection using the HPC data.
So the problem statement is that current systems is on depend on signature-based detection and cannot detect new or unknown attacks and detect ransomware too late. So because of this delay, data is already encrypted before detection. So our motivation is that ransomware attacks are increasing rapidly and causing major financial and data losses. So we need a system that is real-time and accurate and has low overhead. So that's the main idea behind our project. So methodology of our project is first we collect CPU level data using hardware performance counters, and then we extract features like CPU cycles, catch misses, instruction count. So after that we pre-process and label the data. Then we train machine learning models using the data. So finally the system detects ransomware in real time and displays the results through a graphical interface. So algorithm in our project, we use three models: random forest, support vector mission, and logistic regression. Among these, random forest performed the best. It combines multiple decision trees and improves the accuracy. So this diagram shows the overall flow of the system. It starts with data collection and then processing, followed by the model prediction, and finally real-time monitoring. So we tested our system using more than 1000 files, including both normal and ransomware files. So our model achieved around 97.85% accuracy, high precision and recall. So the key observations we found is HPC data clearly helps distinguish ransomware and real-time detection is possible. So system overhead is low. However, there are some limitations like smaller dataset and control testing environment. So to conclude, we developed a real-time ransomware detection system using HPC and machine learning. The system achieved high accuracy and can detect even advanced ransomware early. So in future, we can improve this by using larger data sets, adding cloud-based alerts, and deploying in real-world environments. So these are the references we have. So thank you, ma'am.
Thank you so much, sir, for your presentation. Now I'd like to invite our session chairs for any questions.
I would like to ask regarding the HPC, but the university standard abbreviation for the HPC is the high performance computing, and how you are going to utilize the same with the hardware performance counters, and what exactly mean by counter here? Over to you.
Okay, sir. Thanks for the question, sir. In our project, HPC does not refer to high performance counting. Here, HPC means hardware performance counters, which are special registers inside the HPU. These counters are used to measure low-level activities happening during program execution, such as instruction count, CPU cycles, catch misses, and branch mispredictions. By countering, we mean counting how many times these events occur while a program is running. So when ransomware executes, its behavior at the CPU level is different from normal programs. These differences are captured by the counter. So we collect this data and use machine learning to identify whether the activity is benign or malicious in real time, sir.
So what metric or what methodology you have used to just identify these activities, and how you are going to measure these activities if something misses, that ransomware is going to be identified, and what the normal algorithm which is going to be executed. So what are the various metrics which you have used to count this activity?
So our main technique is a behavior-based detection approach using hardware performance counters and machine learning. We collect HPC low-level CPU data using HPC and which captures how a program behaves during execution. And then we use machine learning models, especially random forest, to analyze this data and classify whether it's normal or ransomware. So instead of relying on signatures, our system identifies ransomware based on its execution behavior patterns in real time, sir. Sir,
Thank you for your
Okay,
answer.
thank you.
thank you, sir.
Ma'am, do we have any questions from your end?
Yes, can I?
Yes, please, ma'am.
I'd like to know, how do you plan to validate the robustness of the system on unseen ransomware families or real-world workloads, as you have a controlled data set from now?
Yes, ma'am.
Sorry?
So in our project, we did not design it as a service ma'am, with multiple plans. Instead, we developed it as a single prototype system for a ransomware detection ma'am. So this system continuously monitors CPU behavior using HPC and classifies its activities ma'am, in real time. So in the future, it can be extended into different service levels such as basic monitoring, advanced analytics, and level security solutions ma'am.
Okay, thank you.
Okay, thank you for your time and attention.
Thank you so much for your presentation, sir. Now I would like to call upon our next presenter. Our next presenter is S. Lalita Gitanjali, presenting a paper on the title Real-Time Road Risk Assessment Using Segmentation, Guided Multi-Object Tracking, and Alert Classification. I request you to kindly take over with your presentation, ma'am.
Yes, ma'am. Is the screen visible now?
Yes, ma'am, it is visible.
Good afternoon, everyone. I'm Lalita Gitanjali from VNR Vignan Jyoti Institute, Hyderabad, India. I'll be presenting on a work titled Real-Time Road Risk Assessment Using Segmentation-Guided Multi-Object Tracking and Alert Classification. This work focuses on improving road safety using computer vision and artificial intelligence, particularly in challenging real-world traffic conditions. Road safety remains a major concern, especially in unstructured traffic environments like in India, where pedestrians, cyclists, and even animals share the road. To address this, we proposed a real-time road risk assessment system that processes dash cam videos. Our system integrates multiple components like object detection, road segmentation, and multi-object tracking. In addition, we introduced a fusion filter to reduce the false detections and a perspective-aware danger zone and a risk metric which is called RIRS score. Overall, our system provides accurate detection and reduces the false positives and generates meaningful alerts in real time. Our problem statement is road accidents often occur due to unexpected intrusion of road users like pedestrians, cyclists, and animals. This problem is more severe in unstructured traffic environments where there are no strict lanes, rules, and objects can appear suddenly. Existing systems have several limitations. They generate high false positives. They provide only binary alerts like safe or unsafe. They do not integrate detection, tracking, and risk evaluation together. Because of this, the current system failed to accurately assess the real world risk. So there is a need for a system that can understand the scene, track the object movement, and provide continuous risk evaluation. The objectives of our project is to develop the real-time road risk assessment system for the pedestrians, cyclists, and animals to perform semantic segmentation, to identify the objects which are moving, to track the objects, and filtering using the fusion and compute the RIRS score to give the alerts such as caution, warning, and critical. Now I'll explain how our system works step by step. Our system follows a pipeline, which is the first one: detection, segmentation, filtering, tracking, road risk assessment, and alert generation. The methodology is that first we give the dashcam images, which are captured real time. And then the first thing is the YOLO VM model detects the objects like pedestrians, cyclists, and animals. And then the segmentation performance takes place, like segmenting the roads and non-road things. And fusion filter, which removes the false detections using vehicle overlapping and ground contact verification and improves the road mask overlapping. And next, the object tracking, where we track the objects by using bytrack, and by using Kalman filter, we will have the prediction of the motion. And we will have the RIR score. Based on all these values, we will calculate the RIR score, which is based on the distance, speed, and position, which we got from the previous pipeline. And finally, the alert generation takes place depending on the RIR score, which is caution, warning, and critical. This is the detailed system architecture. The first thing is input video of the dash cam, where the frame extraction takes place. The system takes the dash cam video and converts into the individual frames. Because deep learning models doesn't process the images, so doesn't process the videos, they process the images. Each frame is processed sequentially, enable real-time analysis of the scene. And the next one is object detection, where we have YOLO V8. It detects the pedestrians, cycles, and animals, where it provides the boundary boxes and class labels. It processes the entire image at once and extract the features like edges, shapes, and textures, and then predict the objects. Next thing is multi-object tracking, which is used, which is not called by tracking. By tracking assigns the unique ID to each of the detected object and tracks it across the frames. It matches the objects between consecutive frames based on their position and similarity. This helps in understanding the object movement over time instead of treating each frame independently. The next module is segmentation, where we have used a segmentation format B2. It identifies the road and non-road region by analyzing the image at pixel level. The next one is fusion filter. The fusion filter removes a false detection and keeps only valid road objects. It eliminates objects overlapping with the vehicles, and it checks if the objects are touching the road and verifies that they lie within the road region. This significantly reduces the false positives and improves the system reliability. The next one is tracking and motion, which is used by a Kalman filter. The Kalman filter predicts the object movement and smooths the tracking trajectories. It uses the previous object positions to estimate the next position and corrects it using detections. It also helps estimating the speeds of the object, which is important for the risk calculation. The next one is danger zone. We did it as a trapezoidal zone, which is in front of the vehicle to represent the risky area. This shape accounts for the perspective where closer objects appear larger and more critical. The system checks whether the object falls inside this region to assess the importance. RIRS score, it is based on the distance, speed, and object position. The final output is annotated video showing object detections, tracking IDs, and alert levels. The novel contribution one is RIRS score, which novel contribution one is a vehicle overlap filter and ground contact verification, mask overlap ratio, which is a fusion filter. Detection alone produces many false positives, such as objects that are not actually on the ground. To address this, we applied a three-stage filter. First, we perform a vehicle overlap to check removing the detections overlapping with the vehicles. Second, we perform ground contact verification, ensuring that the object is actually touching the road surface. And third, we use road mask overlap check, where we verify how much the object lies within the segmented road region. Only objects that pass all these three checks are considered valid. The next one is danger zone and IRRS score, which is RIRS score is 0.5 into 1 minus D plus 0.3 into V plus 0.2 into Z. It combines the distance, velocity, and position into a single risk score between 0 and 1. Distance is estimated using the object size. Objects which are closer appear longer and more dangerous. So it is given the highest weight, which is 0.5. Next, the velocity is obtained from tracking. The faster objects increase risk, so it is given moderate importance of 0.3. The zone depth represents where the object lies inside the danger zone. So it refines the spatial relevance, and it is given the lower weight, which is 0.2. These values are normalized to keep the score consistent and conservative. Based on the score, alerts are classified as caution, warning, and critical to provide the gradual risk indication instead of binary output. These are the results which we got. The slide presents the performance of the proposed system along with the ablation study to show the contribution of each module. The table shows the for three classes like pedestrians, cyclists, and animal. Precision indicates how many detected objects are correct. Recall indicates how many objects are detected, and F1 score represents the balance between them. The system performance is best for the animals with higher precision and recall, while the cyclist performance might be lower due to smaller size and variations. Overall performance achieved is the precision is 0.82 and the recall is 0.72. FN score is 0.76. MAP at 0.5 is 0.2 and MAP at 0.5 is to 0.95 is 0.6480. The ablation study shows how each module improves the system performance step by step. Using only YOLO V8 detection gives a baseline performance of 0.69, which shows detection alone is not at all sufficient. Adding conformer based road filtering increases the performance to 0.750 by removing off-road fault detections. And incorporating ByteTrack further improves the performance to 0.775 by maintaining object identity across frames. And the full system with Kalman filter and IRS achieves the highest performance of 0.7985. This shows that each module contributes incrementally to the final performance. And this is the output which we got from the video. Left side one, which shows the pedestrians. There is a critical alert where pedestrian is very much closer to that, to our car. And the right side one is the warning, which they might be intruding us. Coming to the conclusion, we proposed a real-time road risk assessment system using dashcam video. The system contributes detection, segmentation, tracking, and risk modeling. And we introduced a fusion filter to reduce the positives and perspective-aware danger zone for better spatial understanding. We also developed RARS metric for continuous risk evaluation. Thank you.
Thank you so much, ma'am. I would like to ask our session chairs, do we have any questions from your part?
No question from my side. Nice work and presentation.
Thank you so much, ma'am. Dr. Sangwe, sir, do we have any questions from your end, sir? All right. Thank you so much for your presentation, ma'am.
Thank you.
Now, with this,
I am audible. One
yes,
minute.
sir,
One
yes, sir,
minute.
yes, sir, yes, sir.
So one question is from my side is at the
Yes.
time of rainy season, how the visualization is going to be done?
Sir, how
Either
the
this type of risk you have considered at the time of rainy season, how that roads are going to be visualized, what type of mechanism you are going to put in your research work?
Yes, sir, in rainy conditions, the system still follows the same pipeline, but the performance can be affected due to reduced visibility and reflections. YOLO and SetFormer are trained on diverse data sets, so they can handle moderate variations, but heavy rainfall may reduce the detection accuracy. However, tracking with ByteTrack and Kalman filter helps maintain the object continuity, even when the detections are temporarily weak. So overall, the system works in rain, but accuracy may decrease if it is very high rainfall. And improving the robustness to such conditions can be considered in future work, sir.
So, are you happy with the answer? So, all right. It seems like there is some technical glitch.
Yes.
Thank you so much, ma'am, again for
Thank you,
the
ma'am.
presentation. Thank you.
Thank you.
I would like to call upon our next presenter. Our next presenter is Ms. Sula Deyaratne, presenting a paper on the title TAB Explain Generative Conditional Sampling for Explainable AI in Tabular Data. I request you to kindly take over with your presentation, sir.
Hi, am I audible?
Yes.
Okay, let me. Can you see my screen?
Just a second, sir. Yes, now we can see the screen.
Okay. Good afternoon, everyone. My name is Natula Dayaratna, and I'm from School of Computing at the Informatics Institute of Technology, Sri Lanka, affiliated with the University of Westminster, UK. So today I'll be presenting Tab Explain, a framework for generative conditional sampling applied to explainable AI in tabular data. And my co-author is Mr. Guhanathan Poravi. So let me start with why this work matters, why most of the current XAI methods fail. So when we deploy machine learning models in critical domains like healthcare, finance, or insurance, we need to explain why a model made a particular decision. So the go-to methods for this is kernel shap, line, and methods like that. So which have a fundamental flaw, which is they assume features are independent of each other. So, but in real world tabular data, features are almost never independent. In healthcare, in health, for example, in a healthcare data set, age, BMI, and blood pressure co-vary. And in a finance data set, for an example, in a loan prediction data set, the features like income, debt, and credit utilization are structurally linked. So when these methods ignore these correlations, they create synthetic data points that could never exist in reality, and then ask the model to make predictions on these impossible inputs. So these dangerous consequences is that correlated but non-causal features got inflated important scores. So a doctor or loan officer relying on these explanations could end up focusing on the wrong features entirely. So TabExplain addresses this by replacing independence-based marginal sampling with a learned conditional generative model that respects the true joint feature distribution. So the framework operates in 3 stages. So first, we train a conditional WGAN GP, which is a versatile generative adversarial network with gradient penalty that learns the relationship between features from the training data. Second, we need to estimate what the model would predict with only some features known. So we use Monte Carlo sampling with 200 conditional imputations from trained generator. Third, we aggregate these into final Shapley attributions. So using exact computation for up to 15 features and a weighted least squares approximation beyond that. So let me briefly walk through the architecture. So first, the generator takes 3 inputs concatenated together, the observed feature values with zeros at unknown positions, a binary mask indicating which features are observed, and later noise vector. It processes these through residual blocks with batch normalization and output realistic completions for the missing features. And then the discriminator or critic in WGAN terminology takes a complete feature vector along with the mask and outputs an unbounded score. So we train them with versatile loss plus a gradient penalty for stable training. And importantly, we add a reconstruction loss that ensures the generator accurately reproduces non-feature values. We also use multi-initialization strategy to mitigate sensitivity to random seeds. So a key contribution of our work is the evaluation protocol itself. So prior explainable AI evaluation studies often rely on single metric, which can be misleading. So we propose 5 complementary metrics that together give a holistic picture of explanation quality. So MAE measures how close the estimated Shapley values are to the true ones. And second, the correlation value MSC checks whether the underlying correlation estimates the building blocks of Shapley values are accurate. And third, the Spearman rank correlation tells us whether the feature importance ranking is preserved. And the sign accuracy checks whether we get the direction of each feature's contribution right, positive or negative. And finally, the sensitivity F1 measures how well we can distinguish truly important features from unimportant features. So now for the results, on our 4-feature synthetic dataset, where we have analytical ground truth, TabExplain achieves 7.26 times lower MAE than kernel shap, which is good, and a 9.14 times lower correlation value MSC, and a Spearman correlation of 0.923 versus 0.612. So So looking at our full four method comparison, we see a clear hierarchy that directly corresponds to the quality of dependency modeling. In Lime, with no dependency modeling at all, performs worst, and kernel SHAP with marginal sampling does somewhat better. And empirical conditional SHAP, which uses k-nearest neighbor conditioning, achieves a meaningful 2.5 times improvement over kernel SHAP, but conditioning leads across every single metric. So notably, kernel SHAP's sign accuracy of 0.5 on this 4-feature dataset is barely above the chance of level of 0.5, meaning it frequently gets the direction of feature contributions wrong. So to test the scalability of our explainable AI method, we evaluated on a 20-feature dataset with 5 highly correlated pairs. So here the independence assumptions becomes catastrophically violated, and kernel SHAP's Spearman correlation drops to 0.503, and essentially random rankings. Even more critically, its sign accuracy falls to 0.364, which is below random chance, meaning it systematically gets directions wrong. So TabExplain maintains a Spearman of 0.8 and sign accuracy of 0.7, demonstrating that our weighted least squares approximation with 500 sample collisions scales effectively. So to summarize our contributions, we propose TabExplain, a novel framework that integrates conditional doublegund GP with Shapley value computation. And we have introduced a 5-metric evaluation protocol for holistic explainable AI assessment. And we have demonstrated a 7.26 times improvement in attribution accuracy, validated up to 20 features. And the framework is fully open source and in Python and PyTorch with no dependencies, no proprietary dependencies. So in future work, we plan to extend TabExplain to handle mixed continuous categorical features and integrate with causal discovery methods and validate on real-world clinical and financial datasets with domain expert validation. And yeah, thank you. Thank you for your attention. I'd be happy to take any questions.
Okay, sir, you have done a very good work. And my question is, what type of data set you have used for your research work?
Yeah, for this
And
method,
what are the number of samples which you have considered and the type of data set?
Yeah, the main data set we used here, sir, is a synthetic data set where we already know the true Shapley values of. And I used 2 data sets of them, one with 4 features and another data set with 20 features. That's an experimental setup, to say. Yeah, and I've tested my method on 3 data sets, 3 real-world data sets. One is a lending club data, which is a famous loan prediction data set, and other 2 data sets from medical domain.
Okay, thank you.
Thanks.
I have a question, and I'd like to know how sensitive is TabExplain to the quality of the conditional generative model?
Yes, our evaluation protocols shows that it has a good level of sensitivity because we achieved a good sensitivity F1 score. And because these are in our initial stage, we are testing this with synthetic experiment, but we have achieved a good sensitivity, but we are planning to scale it to more real-world data sets. For now, it has maintained a good level of sensitivity.
Okay, thank you. Good work.
Thank you. Thank you.
Thank you so much. Moving on, I have our next presenter. Vedant Vipin Joshi presenting a paper on the title, A Multimodal Framework for Integrated Software and Hardware Project Orchestration. I request you to kindly take over with the presentation, please.
Yeah, thank you. Am I audible properly?
Yes, sir, you're audible.
Okay, sure. Let me share my screen. Okay, is it visible properly?
Just a second, sir. Um, right now, I can't see your screen.
Just a second. Let me try resharing it once again.
Just give it 1 second. Yeah, now it is visible.
Okay, it's visible, right?
Yes, sir.
Sure. So first of all, thank you for providing me the opportunity to present our research work, which is titled as Multimodal Framework for Integrated Software and Hardware Project Orchestration. So I am a student from Pune Institute of Computer Technology, and this work was co-authored by my colleagues Sanchit Joshi and Aditya Mangalekar, along with our Professor G.S. Mundada. So today basically we will explore how we can finally tear down the operational walls between the software developers and the hardware engineers using AI and IoT. So moving forward, let's start with the core problem facing modern engineering companies. Today, operations are heavily compartmentalized between in the software teams. Uh, Basically, the software teams work using the agile methodologies in today's world, which are basically fast, iterative, and they work on sprints. On the other hand, the hardware teams, which mostly follow the waterfall approach, which is rigid, linear, and it depends heavily on the physical supply chains. And because of the two worlds operate completely different planning cycles, we see a massive clash between them. And this lack of integration leads to wasted administrative resources, inconsistent cross-domain data, and ultimately leads to severe delays in a product's time to market. Moving forward, to solve this, we came up with a solution and developed an application named SaaS application named as Converge, which is basically a hybrid project management SaaS framework. Converge is designed to bridge the gap between the agile and the waterfall workflows without forcing one team to abandon their preferred methodology. It also allows software teams to look at the agile Kanban boards while hardware teams look at the waterfall Gantt charts, but the underlying data which they are observing is exactly the same. We achieve this integration through the using the three core pillars, which is the first is the multimodal documentation, where the AI processes the video and text records, and the second one is real-time state synchronization, keeping all the teams updated instantly, and the third one is the IoT oriented task automation, which allows physical hardware to trigger the software updates. Moving on to the system architecture, uh, looking at our system architecture, we utilized Next.js as the front end, which will be the client-facing interface to ensure fast, optimistic UI updates. And the backbone of our uh, application is the Supabase, which handles database and the real-time engine. So let me give you an example. If an engineer drags a task card on their screen, the Next.js front end instantly updates the UI for the user and in the background it sends a secure message to the Supabase to update the database, and the Supabase utilizes the WebSockets to instantly broadcast the state change to other connected engineer, ensuring absolute cross-domain data consistency. So our AI-driven multimodal documentation basically relies on three things, which is video summarization, text summarization, and end-to-end workflow. One of the biggest bottlenecks in engineering is manual reporting. To eliminate this, we integrated an advanced AI pipeline for multimodal documentation. When a user uploads a technical report, say for hardware inspection, our system triggers a Python or Fast API backend for which we use RESTnet 50 as a feature extractor to analyze the spatial content of the frames, combined with bidirectional LSTMs to preserve the context for it and evaluate the dynamics. And this video summarization model achieved a impressive score of 83%, and simultaneously we also passed the AI audio through the uh, transformer models like BART or T5, like depending upon the requirement, and then summarize them and achieved a score of 0.42. In short, the system watches the meeting and writes the report for you, basically eliminating the manual work for the engineers. Moving forward, uh, to further close the gap between the physical hardware and the software repository, we developed IoT oriented task automation. In a traditional startup, a hardware engineer finishes a physical task, walks over to a computer, and then logs the update. But what we did is, in Converge framework, the hardware itself does the logging. Whenever a hardware component, for example, an ESP32 module, completes a physical operation, it executes an HTTP post request directly to our backend API, and Supabase immediately registers this and pushes the update using the WebSockets over the UI, and the updated UI is updated accordingly, and the work is done autonomously.
Vedant, sorry to interrupt you, Vedant. Some rectangular strip is appeared in your presentation. Entire presentation is not visible properly. Some rectangular black color strip is appeared on your screen.
Is
Yeah,
it
here
visible now?
also the same.
See, your screen is visible. What sir is meant to say is there's some sort of a glitch basically, because what you're showing is seen to us. However, there is some barrier. If you can just
Just a minute.
share.
Yes, I'll try it once again. Just a minute. Is it visible or the problem still exists?
It does still exist.
Okay, continue. Anyhow, right.
Sorry for the inconvenience. I don't know actually why is the technical glitch occurring. So yeah, continuing with it. In traditional setup, a hardware engineer finishes a physical task, walks over to the computer as I mentioned, and logs the update physically. So in Converge, what we did is like use the ESP30, for example, a ESP32 module completes a physical operation, and then it sends a HTTP post request directly to the backend, and the Hubase registers this update and then updates the UI accordingly autonomously. So now let's discuss the project planning. So estimating how much effort a task will take is difficult. Like it is basically done on depending upon the gut feeling of the manager. So traditional deterministic models often also fail because they don't adapt to the agile team's unique uh, velocity. So to solve this, we implemented a hybrid machine learning model using ensemble learning. Like what we did, we used a random forest algorithm, and we found out that depending upon the lines of code and development time required, the lines of code had 34% impact on the accuracy of it, and along with the development time, which were our strongest predictors. By feeding this historical data to our model, we were able to cut the mean magnitude and the relative error from 0.68 to 0.32. So moving forward, for backend, uh, we used is video uploading for the hardware project management. So in traditional HEVC encoding scales exponentially due to brute force mode decision, and which is a computational bottleneck. So we had to optimize our backend to prevent storage bottlenecks. So traditional compression uses brute force encoding, which requires exhaustive rate distortion, optimization, search. So our innovation was to deploy convolutional neural networks to optimize the HEVC encoding, which is based on classification instead of search, and this resulted in an 61.8% time savings during the video encoding, with nearly almost very low penalty of 2.3%. So by automating the video summarizations and utilizing the IoT triggers, we reduce the time engineers spent on manual documentation by approximately 60%, and it allowed a massive shift in sprint time allocation back to core engineering and development. And despite the heavy multimodal data, real-time engine managed to synchronize the cross-domain assets with a system latency of less than 200 milliseconds, ensuring completely seamless collaboration. And to conclude with this, the Converge unifies the agile software and waterfall hardware workflows without compromising the integrity of bill of materials or digital repositories. Our AI integration successfully shattered the semantic search barrier for documentation, and our IoT pipeline created a truly autonomous status tracking environment. So moving forward to the future scope, we can expand our predictive ML models to include automated hardware dependency tracking, automatically flagging the hardware software conflicts before they happen, and extending our IoT integration to edge devices. So thank you everyone for your time, and I would be open for any questions.
Thank you so much for your presentation, sir. I would just like to ask our session chairs if we have any questions.
This is the framework with what exactly the objective you want to achieve through this research? Veda?
So the gap between the hardware and the software management life cycles, like there was over dependency, and the tools all present in the market were basically all leaning towards the software management life cycles. So our agenda
there
was
is
to
some
bridge the.
So there is some network issue because we cannot hear you clearly right now. You're audible, however, your voice is cracking. Hello? Yes, so that's what I'm saying. You're audible, however, your voice is cracking. No issues. You continue with your answer. Maybe possibly we'll be able to listen to you.
Sorry for the inconvenience. Actually, there is some network issue, I guess. So
Okay.
I was basically trying to say that we are trying to bridge the gap between the software and the hardware project management. Like the hardware project management also for in case of IoT devices or any developing any hardware project also requires software code to be written along with it. So we were trying to bridge the gap between the two teams. Like software teams generally follow the agile methodology, and the hardware requires supply chain management and trial and error things. So we were trying to bridge the gap between them basically.
Okay, thank you.
Thank you, sir.
Ma'am, do we have any questions from your end?
No question from my side. Thank you.
Thank you so much, Sir Vedant, for your presentation. Okay. Now I would like to call upon our next presenter. Our next presenter is Sheikh Janbhasha presenting a paper on the title Multimodal Deep Spatio Temporal Framework for Automated Crop Mapping and Yield Prediction using Sensor Images. I request you to kindly take over with your presentation, sir.
Thank you, madam. Thank you so much. Am I audible, madam?
Yes, sir, you're audible, sir.
My screen is visible, madam?
Yes, sir.
Okay, thank you, madam. Thank you so much. Sorry for the inconvenience. Due to an urgent meeting, I could not present my paper previous session. So, very good afternoon, sir. So, this is Sheikh Jan Basha. So, currently working in the Civil College of Engineering, Hyderabad, India. So, my paper ID is 1087. The title is Multimodal Deep Spatial Temporal Framework for Automated Crop Mapping and Yield Prediction using the Sensor Images. So this is the agenda I'm going to discuss. The abstract, the introduction part, some of the literature survey has been done on this topic, and the research gap, what I have found, and based on the research gap, so I propose the methodology followed by the results and conclusions with the references. So for every country, agriculture is the backbone. And this is one of the crucial economic stability and livelihood and food security. And the agriculture is facing the number of challenges due to the population growth, the climate change, and limited land. So for this, the remote sensing enables the largest scale. Sorry. This one I have to present here. Real-time crop mapping and yield prediction are the essential for the agriculture planning, food security, and the climate resilience. So for this, the traditional field surveys are very slow and costly and inconsistent, limiting large scale monitoring. So to overcome this one, the existing some of the remote sensing approaches, existing remote sensing approaches are using. So even though they are facing some challenges such as the cloud interference, temporal model limitations, and mixed pixel issues. And existing methods completely focus on what we call the unified framework for the current research lacks unified framework, but integrates the multispectral SAR and finversal data efficiently. Means that some of the methods only focusing on the multispectral, and some of the methods only focusing on the SAR, and some are focusing on the phenological data effectively. And by integrating all these methods, so I have proposed a unified framework. So that is the multimodal deep spatial computer framework. So which combines some of the deep learning models, CNN and LSTM, attention-based TCN, and then the multimodal fusion. So because of this one, we can enable the accurate and the scalable crop monitoring and yield prediction. This will be useful to the farmers and the country also. But agriculture, coming to the introduction part, agriculture is crucial for economic stability and here for the livelihood and food security. But most of the time we are facing the challenges due to the population growth, the climate change, and the limited land. So with the help of this limited land, the climate change, by considering the population growth, so we have to consider to grow the agriculture. For this reason, the remote sensing enables larger scale multi-temporal crop monitoring. So this includes all weather imaging sensors. So that is in the form of the synthetic aperture radar. Existing approaches focusing only on individual solutions such as the spatial temporal models, SAR optical fusion, model pixel handling, and attention-based networks. But even though some of the advanced models like multi-GPU unit and phonology-based yield prediction improve the performance, but they are only the task specific. So here, these are some of the motivations so that motivated me to propose this research methodology. Increasing demand for accurate and real-time agricultural information because advanced monitoring system. So nowadays, whatever we are having the technology, so with the technology we enable to increase the demand for the accurate and real-time agricultural information. And existing mapping methods are limited due to the cloud sensitivity of the optical satellite data. So even though we are having some of the existing crop mapping methods, so which are limited due to the cloud sensitivity of optical satellite data. And for this, many deep learning models were used. So they are given good accuracy in terms of the performance, but they are failed to capture temporal dynamics of the crop growth effectively. And a mixed pixel problem also exists in smallholder agriculture, so which will reduce the classification accuracy. So current yield prediction methods rely on simplified indices lacking robust spatial temporal modeling capability. And these are some of the literature survey, some of the work has been done on my related title. So remote sensing, remote sensing basics, CNN BioLSTM or SAR optical fusion, mixed pixel decomposition, CAPs, multi-GPU unit, phenology procedure, and the type of information used is structural, and input data is the different data sets were considered, some of the strengths, the key contribution for each and every method with the help of the corresponding information which has been learned and results and the study. So this is a literature survey table which shows the existing work. And the research gap here, we found the research gap. So based on this research gap only, so we proposed a new method. So here, some of the methods failure to have a single multimodal framework which effectively incorporates multispectral optical data, SAR, BAC, scatter, and methodological data to map props and the predict that using in a comprehensive manner. So a lack of sufficient temporal modeling, where the current system do not reflect the long-range technological dynamics. So this is also one of the gaps. Landscape and pixel hardship in the small folder control areas with unseen deep learning model that incorporates adaptive subpixel conditioning of areas. So scalability also one of the problem because most of the deep learning models they do not really scale to large data sets of satellites. Even the newer systems such as multi GPU or net are also used. The poor association between the classification and the predicting yield. So these are some of the gaps we found on the existing works, which was shown in the literature survey. So this is the proposed methodology. So with the help of this proposed methodology, so we can improve the performance metrics values as compared to the existing method. So here the data is collected from a publicly available data set. And once the data was collected and we pre-processed the data with the help of some of the tools which are available on the web. And from that pre-processed data, so we extracted the multimodal features. And from this extracted features, so we are given to the spatial controller deep learning model. And after that one, we given they decomposed the mixed pixels. Then finally, the output was presented for the cross segmentation of the information. So this is about each and every module which was presented in the proposed methodology. So here I use the data set which is publicly available data set, the Radiant ML Hub Prop classification data set, and which is the combination of the multi-temporal Sentinel-1 and 2. So imaginary with the pixel level crop labels. And once the data set is taken and that will be pre-processed, so data will be pre-processed. So here optical data is corrected. Yeah, and here we have normalized the data with the help of some of the source built-in technique. So after that, we applied the future extraction in the fusion. So for this reason, we have used the CNN and the CNN extract the spectral specific futures. And after that, we use the hybrid bi-LSTM and the channel attention TCM, so which is used for temporal future extracting. And after that one for mixed handling, so adaptive mixed model are missing network estimates the fractional crop areas. And with the help of that, and finally, so we found the mapping and the yield function as the result. For this, we use the UNIS unit. And after that, we have done.
Sir, I'm so sorry to interrupt you. However, we have crossed our 9-minute mark. I request you to kindly conclude as soon as possible, please.
Okay, but this is the result
Yes,
section. So I will conclude. And here, this is the comparative analysis of the existing models with the proposed model. So here we have compared our proposed model with the two existing models, that is the CNN and the LSTM, that are the optical fusion. So as compared to the existing models, so my model performed so very well on accuracy. So accuracy we got a 94.6%. And AUC also we calculated 96, and F1 score also we calculated 91. So this is the result table. So this is the comparative analysis of the existing models with the proposed model. And actually here I have to introduce some of the graphs, but due to the time limit I could not. So this is the conclusion. Here we propose the multimodal deep spatial temporal framework. So that will integrate the multi-scroll SAR and the phenomenological data. And here we used both the spatial and the temporal futures, and both are integrated. And later we use the adaptive mixed pixel decomposition, and which overcomes the cloud limitations using SR imaginary. And here we also use the GPU multi GPU unit segmentation. And here some of the limitations of my work is so the proposed framework completely rely on heavily available large scale, the high quality multi-temporal and the multimodal scale, so which may not be consistently available across all geographical regions. So this is one of the limitations of the my work. And we are focusing on integrating the real-time IoT and the weather data with the framework to enhance the prediction accuracy and enable dynamic real-time crop monitoring and the field testing. So this is the limitation as well as the future work of my proposed method. So these are some of the references I have used and which were I used to write the literature survey. So thank you very much. So any worries on that? Thank you.
Thank you so much for your presentation, sir. Do we have any questions from our chairs?
Yes. Okay. So what the references you have listed now? So these are too much old. You are not referred the latest research papers for your extension of the research work. Okay.
Okay,
Apart
sir.
from that, my one question is, what type of
Sir.
crop sample you have used for your research to test all
Sure.
the parameters?
Here, completely, I have considered what we call leaves, leaf, what we call plant images like that. I have considered.
How many samples you have considered?
So 30,000 samples we have considered, sir. So
How much time?
75.
How much time your algorithm is required to just execute that 30 samples and get the result?
So almost all it has taken 1 hour or 45 minutes. Like it has taken, sir.
Yeah, you have that data. It takes
Yes, sir.
1 hour. You have
Yes, sir. Yes.
not extended your work to HPC machines, so that it is going to be, because when you are going to do the research and if the number of samples you go on increasing, so
Sir,
that
sir.
that much time is we are not going to wait that 1 hour or 2 hours to get the results. And again, if something goes wrong, we have to repeat the same thing number of
Yes, sir.
times.
Yes, sir. Yes, yes, sir.
Try to optimize the time
Sure, sir.
each.
Sure, sir.
Yeah.
Okay, sir. Okay, sir.
Thank you.
Thank you, sir. Thank you, sir.
Good presentation. No questions from my side.
Thank you, madam. Thank you, sir.
Thank you so much, sir.
Thank you, madam.
Thank you. With this, we come to the end of our session. So we'll just call up our absentee. If anybody is there on behalf of sir, I request you to kindly please speak up and take over with your presentation. P.N. Devrocker presenting a paper on design and development of artificial stutter speech corpora. If you are available, anybody from the team is available, please let me know now. All right. So nobody is here, so this paper remains absent. Apart from this, we have completed our session, ma'am, sir. Now I will just do the closing remarks. A sincere thank all our presentations for their excellent presentations and contributions in this session, and all our participants for being a part of this international conference. I hope this session was informative enough. We, on behalf of the whole team, thank you for your support during this 11th version of this conference and all the previous 10 versions of this conference. We will be happy to have you in the 12th version in 2027. All the presenters would be getting their certificates, digital certificates, through email via 2 working days. The publication will be live within 7 to 8 months. Kindly cooperate with the team of ICTIS 2026. I would also like to thank our session chairs. Thank you so much, sir and ma'am, for being a part of this session today. Any closing remarks from your end as you close this session?
So thank you, madam, for your invitation and giving us an opportunity to perform the session chair, as well as we have observed the very good work, good research work from the various researchers, and they have made the very good contribution in the research domain. So I always wish them best of luck for their future research in their interested domain. Thank you, ma'am.
Thank you so much, sir. Ma'am, would you like to say anything before we leave?
Yeah, it was a pleasure and an honor today to be invited as a co-chair, and I want to congratulate all the authors for their work, and I also hope to continue taking part in future editions. Thank you.
Thank you so much, sir, ma'am. This is a token of appreciation. I would like to display it. Professor Sylvia Mchini, thank you so much, ma'am.
Yes.
This is the token of appreciation from our team of ICTIS and Global Knowledge Research Foundation. And sir, Professor Sangwe, thank you so much for both of your presence and sticking through with us without losing your patience over the glitches and the internet connections. Thank you so much for sticking through. I would like all of you all to please switch on to your cameras as we end this session. Let us all have a quick snapshot of this virtual session that we just attended as a memory to keep forever. Requesting all, please switch on to your cameras, all the participants. Thank you so much. Stay safe and we'll meet you in the 12th edition of this conference. Thank you so much for being a part. Thank you.